So you have the handouts. The idea is that we look at a little bit at applications. After doing the theoretical part and learning about wave propagation, to see how some of these concepts are being used in non-destructive evaluation. So very quickly, I'll show you some field testing where resonance frequency and Q factor are being used for non-destructive evaluation. And then I have some examples about wave velocity. We also talk a little bit about attenuation. I guess in your lab report, you kind of now experimentally played with attenuation. So what was your observation? When you changed the frequency, what did you observe?
High frequency, high attenuation.
Right, so the amplitudes became smaller and you had more noise, right? So attenuation is also another parameter that you can use for non-destructive evaluation. And afterwards, then I have to teach you a little bit more theory on reflection and then applications, which a lot of them are in seismic surveys, like geophysical methods, and also non-destructive testing, of course. Okay, I'm not sure if I showed you this before, but whenever you think about wave propagation-based non-destructive testing, I want you always be careful about using the terms. So ultrasonic is being used when we don't hear the frequency of the pulse that you are inputting, etc. A lot of people make this mistake, but if your frequencies are, let's say, below 20 kilohertz, you should not call the test that you are using ultrasonic, because you are not in the ultrasonic range of frequencies. So one of the very kind of famous methods of non-destructive evaluation, at least for concrete, is impact echo. So I talk a little bit about that and then about on different applications of ultrasonic testing. So let me ask you, is there anyone who is familiar with impact echo? Ever heard of it? Heard. Okay, so it's kind of a very simple test, and it's being used extensively now. So let's forget about what you see on the here for a second and just listen to me. One of the very first methods of non-destructive evaluation is sounding. So the sounding is when people just use the hammer and tap somewhere and they just listen to the sound. And based on the sound they were hearing, they would say if, for example, there is a void underneath this wall, etc. There is a funny story that, for example, my mother used to choose a watermelon based on the sound it makes. And there is a lot of science behind it, because if it is hollow, it means that it's very ripe. So this, when the watermelon is very ripe, you have a lot of porosity and a lot of water. So actually, this is a right method to listen to. You are not a civil engineer, but the civil engineers here may have seen that on the bridge, they drag a chain. So they drag a chain, even now, even here, and they just do that, and they listen to the sound. There are people whose ears are calibrated, and just by walking on the bridge and listening to the sound, they kind of can say if there is a hollow sound, if it is not hollow, and if it is hollow, it means that the resonance is coming from a small thickness, and that means that you have some sort of debonding. So impact echo is the objective version of all of these very ancient methods. I don't think I ever told my mom about this. She's not an engineer. So how does it work? Now you can see, let's say, if you go, the way it works is like that. The simplest case is you have a hammer. It normally doesn't look like this hammer. You have some sort of a ball that automatically is controlled with your computer, etc., and it drops a ball, and then you have a geophone or accelerometer very close by. Normally this distance is between 5 to 10 centimeters, so 2 to 4 inches. This distance is not very, shouldn't be very large. Let's say between 5 to 10 centimeter. And what you do is simply you record the response. And then you look at it in the frequency domain. And if everything is okay, you are going to get a single resonance peak which corresponds to the thickness of the slab you are testing. So if the thickness is, let's say, D, this frequency is roughly, so we call this thickness resonance frequency. It's roughly the compressional wave velocity over 2 times d. I'll tell you a little bit more about impact echo when we discuss surface waves. There is a reason why I say it's just approximate, but this approximation works pretty well. So considering that, if we have a situation where you have a layer in between, where you have debonding in your material, whether it is a fracture plane in a rock, or is it a delamination in concrete, what you are recording, depending on the situation, a part of it could be still coming from the whole thickness, but a part of it will come from the resonance of this portion. And since D is smaller, this frequency will be higher. So the frequency is going to be shifted towards, it's going to be shifted towards higher frequencies. So if it was here, it says 6.94, it becomes 7.31. Comes a little bit forward. Now, if you have a situation where you have a very shallow, this should be, for typical impact echo measurements, this should be under 2 inches. If you have a very, very shallow and very large delaminated plane, that is, that's kind of a bad situation. That means that you are close to spoiling. It's close to coming out. Then the mode of vibration changes. This is not being vibrated, the thickness, you are going to record the electoral mode. So the energy goes dramatically towards lower frequencies. It becomes much lower than it was when everything was coming from the thickness resonance. Okay, and then from that, since you know where to expect your thickness resonance, you know where the shallow frequencies are. So when you listen to the sound, it's easy to distinguish this and that. But people have a hard time, if you don't have a microphone or if you don't have a sensor, it would be hard to figure out cases like that. So the subjective ones are still probably okay because this becomes much smaller. If it is really, really low, it can be even 1/3 of that frequency, so you can hear it as a human being. And now there are all sorts of developments in impact echo, so you can just use a microphone basically, and there are rolling versions of impact echo. It's a very, very useful test, and now you all understand what it is. Also look at the signals in the time domain. What do you observe comparing them? We talked about the frequency, but there is also something else you can kind of recognize if you just look at the time domain. Hint. How are they different in terms of attenuation? Right, so for the very, very debonded situation, you actually have energy trapped between the debonded area and your impact, so it doesn't even dissipate. So you see it's even, the second peak becomes larger, and it's very, very obvious. This case, if you do any kind of field testing, this is very obvious. What is not obvious is cases like that in between. Either you look in time domain or frequency, this case is very, very obvious. So this is a very...
Can you
yes.
explain, so you're saying energy is actually getting trapped in that void?
No, it's not a void, it's delamination. It doesn't have to be a void, it's just the two parallel surfaces which are not completely bonded, so you have delamination, for example, because of corrosion.
So where is that energy? So the energy is in between the two different surfaces?
Right, so if you excite this part, then as you can see here, the wave, basically you have a standing wave between the surface of the slab and this delamination. So it doesn't go and attenuate throughout the medium. So that's why the energy doesn't dissipate that easily. Okay. So impact echo is a very, very common non-destructive evaluation technique that is being used. Now, impact echo is not only for delamination detection, also I think it's its strengths, but it's also can be used for different kind of defect. Now, here is honeycombing. So for those of you who are not in materials, honeycombing is when you are pouring concrete, you kind of have segregation. So you have just coarse aggregates, and there is not much fine aggregates in between. And so basically you have a collection of pores over a volume. It can have a completely unusual shape. This is a picture, so you can see how the coarse aggregates are kind of exposed. So you can see that it's only coarse, you don't have much fine aggregates. So the result in terms of non-destructive evaluation is that you are looking for a collection of small pores. So one idea was that, can we detect a defect like that using non-destructive evaluation techniques? So here, this is a slab, a full-scale concrete slab at BAM, where they had generated some sort of simulated honeycombs. So basically, you glue the large aggregates together with a cement paste without any fines. And you glue it and you make an artificial honeycomb, and then you place it somewhere where you know where it is. And in this slab, there were tons of other defects. So it was kind of a reference specimen to go and test different methods. So this one was honeycomb. So when we looked at impact echo and we looked at the frequency shift, as you would look when you were looking for the lamination, we didn't see any changes. So you would get pretty much the same frequency. The difference in the honeycomb would not change the frequency that much. So if you would get this kind of 7 kilohertz, we would get it everywhere. However, if you look at the half bandwidth, if you look at the Q factor, we saw that if you are not at the location where you expect to see a honeycomb, the peak, it happens at the same location, but it has a completely different width. Okay. So other people have used the widths of impact echo signals for freestyle, ASR, DEF, different kinds of damage. This is the experience we had. So if you plot the widths, you see that at the locations where you expect to have these honeycombs, you have wider peaks. Remember, in non-destructive evaluation, you are looking for a parameter which somewhat relates to the type of damage you are looking at. So in this case, the frequency wasn't a good feature. We sometimes call that a feature. But the width was half power bandwidth. So I didn't put any titles for this slide, so you just take time and you just write your own title for it. Like here we see that at the location where we don't have a honeycomb, the frequency peak is very narrow, and the frequency really doesn't change. But at the location where we have the honeycomb, it's much wider. These are real measurements. So, and then when you plot these at all different points where we did the measurement together, you can get a picture of the area. And then you know where those defects are. I'm not arguing that this is the best method. You will see that ultrasound does a much better job. This is just to show you that how some of these things that we have talked about can be used for material characterization. Questions? Discussions?
So you're saying that impact echo can be used, but it's not that.
It's not a perfect method to find. It's really good for delamination detection. Really, really good. It's a very cheap method, so people really like it. Any kind of fracture. If you have a plane of fracture, impact echo is great. If you do it at different locations, it's very easy to use. However, for this kind of applications, it's not as good as ultrasound. One reason is that you can see there is a location problem. Impact echo is a impact-based test, so it's affecting a larger area around it. It's affecting a volume. So the spatial resolution is not as good. Because of that, that's another thing. But it's very cheap. So that's why people use it, and it's very, very popular.
So in reality, can you use half of something to hit the material?
We really don't use a hammer in impact echo. Do I have a picture of our impact echo device? No, I can draw it for you. There are different ways. You can, basically there is a mechanism where you have a sphere, a small sphere, and then let's say there is a magnet, it releases it, and then you have an impact. It's a very tiny impact. It's not really a hammer. This is one of the equipments. Some equipments, they have this same thing inside a device. So they release a ball and then they retract it. And that is the impact. It's very, very tiny. The hammer is just a schematic. No one uses hammer for impact echo. It's cheap and it's very simple.
The last picture, the 3D looking one.
So this is when you do the same thing everywhere and you basically plot the half power bandwidth. over an area. And then you have an image.
They collected this with the magnetic photo?
Yes.
Okay.
And then this is after processing.
So usually this is an area can be tested by this method, like 1.2 meter by 1.
You can test as large area as you want. So there are scanners that you can just mount the impact echo device or ultrasound or GPR on it, and then you define the spacing, and then this was done automatically, so it just goes from one place to the other and it collects the data. Please ask questions. Everyone said you want to see applications, so here are the applications. Ask questions, so let's have an interactive class.
And what if we have like two very large frequencies? So which one do we need to pick to do the analysis?
So this is not the case here, because this is one single slab. You don't get two very large. It has to come from somewhere. I hope that you learn in this class that this kind of resonance, it's coming from some geometry. So if you only have a slab, if you get two, that means that something else is going on. In this case, the frequency wasn't giving any kind of information. You only would get one peak because it's a single slab. Let's look at the picture of the slab. So this is when people are making this a slab. So in this area, there is nothing else but reinforcement and these three honeycombs. So there is nothing else that another peak it can generate. If you see another peak, it means that you have something going on in your slab. There is a situation like that. You don't just get a peak. This is not what's happening. Mm-hmm.
For the part where the delamination isn't too long, like you have reflections both from the end of the slab and you have it from the delamination. Don't they have like two different results on the graph? Because like it's reflecting from two different sections.
Yeah, but they are now kind of overlapping. I mean, these are also real data from actually a real slab. This is not even a single slab. In this case, they're overlapping. You can have two if you have something going on. This is what I was trying to explain. If you see two peaks, it means that you have something which is causing that second peak. So if you have two peaks, one a high frequency, one is still here like that, it means that you have a boundary inside. Okay. So what we did for honeycombing is we just focused on the whatever you would get at the location of the thickness of the slab. We had nothing else anyway, but you just look at the thickness resonance and you look at how wide it has become. So basically you just look at attenuation because the change of frequency didn't give us much information. Is it clear?
It's just it's interesting for me why they overlap the two. Like,
because they are not that much.
if they were really far from each other, that would.
One is 6.94 and the other one is 7.3.
But if they were really far, they would have. Like
Yes,
yeah.
yes. So you can get something like that. I mean, you can see here also that you have a little bit more for the second harmonic. I mean, you have a double of this here, a little bit energy. I don't really recall exactly what this testing was about, but you have a situation like that. You can have. So what you do in that case is you look at different. So you plot this. You plot everything as a function of depth, for example, and then you look at different depth. And then you will see whether you have anything between the bottom of the slab and the surface. Then you will see this peak. This was not the case in these measurements. We didn't have any other peak other than this one because there is no delamination inside. Okay?
Experimentally, it seems like the test is kind of strange. Even if you took the same material, like you had concrete that was of the same mixture, let it harden, and then you just put it in there, and then you poured fresh concrete over it, wouldn't this be able to identify those positions of that? Like in this picture, like you can clearly see the darker spots. Yeah, not the
This-
image. Yeah, this image.
This is coming from the edge. So when you have impact echo, this is the edge of the slab. The problem is if you are very close to the edge, this is also acting as another boundary. So you are going to see some sort of a peak coming from that. And the worst part is when your distance to this edge and your distance to the thickness is equal. So you have to avoid this kind of edge areas. That's what I said, that it doesn't have a good spatial resolution because it affects a volume around it. So if you go towards the edge, you get artifacts. There is no perfect method for anything. So for everyone, you have to understand what it does and to be able to interpret it.
I was kind of more concerned with you can see the black, like you can see the square, the circle, and then the sideways cylinder.
Mm-hmm.
So did they put that on there? This is actually from.
Oh, this the shadows.
Yeah, the shadows.
This is just for visualization.
Oh, they did.
No,
that.
you don't see this
okay.
in the. This is my own work, so I know how this has been done.
Okay, because I was just thinking, because the way that you explained it is as if they, took this pre-made material and then just stuck it in different places. But if you were to even take the same material of the same mixture without honeycombing, wouldn't it be able to identify those? Like say those.
If there was no honeycombing,
Mm-hmm.
you would not see areas which were like that.
So it didn't create some sort of boundary by making it pre-made and then pouring new over it?
It's not because it created boundary, it's because it attenuates. So when you have this kind of honeycombs, it attenuates the wave a lot more than when you don't have, because you have these pores inside.
Okay.
And because of that, the width becomes larger. And because of that, at those locations, you are going to see that. Again, I'm not making the assertion that this is a very good method for this application.
Okay.
This is just to show you that this can work. But for this application, this is a little bit too rough from my perspective. Especially, I mean, the things Tiffany was asking is kind of important. I can't tell you all the details, but a big problem in non-destructive evaluation is false positives. So if you get these indications, this is nice, but you also have these other indications. For example, if I didn't know that there is nothing here, wouldn't I have interpreted this as a defect? Yes. So now the boundaries, we understand why, and here there was another thing, that's why you see that. The boundaries for impact echo, we understand why you would get that. Because when you are close to the boundary, you also get reflection from the boundary, so the peaks become wider. So that's why this is also larger. But that's a false positive. And that's always, in practical applications, it's always a danger. Where is that coming from? Okay. Now this is all I wanted to show you about this kind of testing with resonance. Now, just a kind of recalling from what you have learned so far. Please label at least these two waves and try to write down the expressions for velocity, if you remember. So the direction of propagation is from left to the right, and the arrows you see, they are particle displacement. Remember that in 3D and 1D we have two expressions for P wave, right? I hope that you all recognize this is a compressional wave or P wave. In 3D, that's the expression for the velocity. We already derived that, so you have seen this before. And then here we have S wave. We have talked about this also at length. And this one always has this velocity, square root of g over rho, no matter if we are in 1D or if we are in 3D. Now, how about this one? The one on the top. What type of wave is this? Surface wave. So, so far, we looked at one-dimensional longitudinal. We looked at bulk waves inside three-dimensional space. We haven't really looked at what happens at the boundaries, but this is kind of giving you a flavor. So if we have a free boundary, we have other kinds of waves. One of them, which is very important, is surface wave. So this wave is also called, it's better to call it Rayleigh waves because we have several types of surface waves. This was discovered by Lord Rayleigh in 1885, long time ago. Also, later on, a lot of work was done by Lamb. If you remember Lamb's constant, in a few years after, in 1904. Now, without going to any kind of theory today is just about application, so I try to stay away from too much equations. We need to know a few things about surface waves. First of all, they occur at the surface. Look at the particle motion. So, what do you see? Go ahead.
Just like you have the arrows, so they're probably like.
The arrow is the other way. You see?
It's like just circling, like they're circling as they go.
Yeah, so it's a retrograde ellipse. It's going like that. So because of that, you can see that you kind of have both components. You have a component, a shear components. Look at the elements. You can see that they are distorted. The angles are not 90 degrees necessarily. So you have a shear component, and you have also a compressional wave component. You also see that they are getting compressed at some locations and stretched at other locations. So Rayleigh waves, they have two components. One is a vertical component, similar to SV, and then one is a horizontal component, similar to P. If you look at the theory, which we will look, it's basically a combination of P and shear wave at the surface. That's why it looks like that. In terms of velocity, I don't know if any of you has ever done anything with surface wave. You have done, right? So is it faster than shear wave or slower?
It's a little bit smaller than shear wave.
Right. So Rayleigh waves are, the velocity is between 0.933 times Vs. This is when the Poisson's ratio is 0.5, and the lower bound is 0.874 Vs for these are the extreme cases of 0 and 0.5. So the rule of thumb for earth materials and concrete is that we kind of take it to be 0.9 Vs. It's rule of thumb, a little bit slower than Vs, as Ian just mentioned. The vertical component is much larger than horizontal, and generally speaking, the amplitude is much larger than the other waves on the surface. So why I'm saying that, because we want to look a little bit into attenuation that you experimentally looked at. Let's look here first. So when we have any kind of impact, or when we input some energy into the material, so here is, let's say, where your hammer is. If you don't control, like we do in ultrasonic testing, you generate different kinds of waves. So the one on the surface is, of course, Rayleigh wave. So it's propagating here on the surface. And then we have shear wave and compressional wave. This diagram has a lot of information in it. But what I want you to pay attention to are, first of all, let's look at compressional wave. The large sphere that you see, this one, this is the wave front of the compressional wave. This is spherical, as you can see. Its maximum just underneath your load. So as you can see, the maximum is just here, and then as you go towards the surface, it becomes smaller. So what you see, this band, it shows you the relative amplitude. Shear wave is different. The maximum occurs not actually in the middle, but at some angle, about 40 degrees in that window that you can see. That's where the maximum shear wave is happening. And it's also spherical. What you should notice that as you go away from the source of impact, the energy is being spread and spread over larger and larger spheres, for example, for P wave and S wave. Because of that, since the amount of energy was constant, since it's getting spread over larger and larger spheres, it becomes the wave amplitude becomes smaller and smaller. This is one mechanism of attenuation, which is called sometimes geometrical spreading or attenuation. So meaning that we have attenuation just because of geometry. This is one form of attenuation. If you measured, for example, in the lab, you measured over 3-inch thickness, correct? If you use the same setup and your thickness was 5 inches, everything the same, your amplitude would be smaller. Just because of this geometry. So there is another mechanism for damping, and that is scattering. Now, this is a little bit different from that one. For scattering, it depends what is the wavelength of the energy you are inputting to your system, and what is the time length scale of the heterogeneities. This is the kind of scattering you experimentally observed in the lab, right? So look what scattering means. Scattering means that the energy, instead of going from the sender to receiver, just like that, it's going to go other places because it gets distracted. In other words, it gets reflected, sometimes a number of times, by heterogeneities on its path. And because of that, it gets away from the path it should have been traveled through, and it doesn't arrive to the receiver as a whole. So it becomes a smaller because it's just going somewhere else. A part of it is going somewhere else. Now, if you increase the frequency, what happens to the wavelengths?
Small.
It becomes a smaller, right? Wavelengths is velocity over frequency. Body wave is not dispersive, so we can assume that the velocity is pretty much the same. So what happens is that when you increase the frequency, the wavelengths becomes smaller, and for the same heterogeneity, it gets more and more scattered by the heterogeneities. That's why the amplitude on the other side becomes smaller. This is what you experimentally measured in the lab. Because in your case, the geometric spreading was the same, right? You had 3 inches, hopefully the same location, so everything was the same. You had some geometric spreading, but the same for all 3 cases. What was different was this frequency. Now, if you have something else in your medium, let's say cracks, this can also increase scattering and increase the attenuation. So it's not only because of the heterogeneity of the medium. When you have damage in the medium, it also contributes to a scattering, and significantly. And because of that, if you see that you have a lot of attenuation, that's also another indication of damage. Okay? And the last mechanism of attenuation is something that we have talked about in vibration before. When we calculated the Q factor for the material in vibration, that kind of attenuation is coming from internal friction. It's coming from the material itself. It can be viscoelastic. That is kind of intrinsic attenuation. We didn't really put attenuation into wave propagation. I probably make a video on that. I don't want to. It's very also mathematically intensive, so I can just show it to you how it is. But it's very similar to what you have seen in vibration. So what happens is that if in the case when we didn't have any attenuation, remember the most general wave equation was something like that. K being the wave number, right? Maybe not writing it like this. T minus x over c. So omega over c is k. I wrote this in different ways before. So in 3D wave equation, if you remember in the video, I derived something like that. So one term is wave number and distance, and the other term is time. Remember?
That's A. That's just the
That's just the amplitude of the wave. So, but we didn't have any attenuation term here. So, if we take attenuation into account, then we have another term added, which can be written in x. This is for viscous damping. This is just what we had discussed before. It's very similar to really vibration. So you will have another term added to your equation, something like that, with x. And you can recognize that, 1/2q, that's d, and you have seen this before. So, attenuation also is a measure that you can use for non-destructive evaluation, because the presence of cracks and heterogeneities also changes these different mechanisms. Geometric spreading, not much, but the scattering and internal friction, a lot. No, I said for non-destructive testing, you have to know about geometric spreading, but we don't use it because that's, no matter what, it's there. But scattering and internal friction are parameters that change if you have some inclusions or some cracks inside the material, and you can use it. Questions? No? So now, I think I've shown you this before in the beginning of the class. Now I hope that this all makes a lot more sense. If we have a sender receiver, if you send at time t0 and receive at time t1, then you can calculate the velocity by dividing the distance over the time of flight. This is what you did in your lab report. Now, if we have a collection of pores, some small pores like that, or it could be also, a lot of small cracks, then what happens is that the velocity slows down. So your arrival time t2 will be larger than t1, correct? And then the amplitude also becomes smaller. So if the amplitude here was a1, here is a2. a2 would be smaller than a1. And the reason is pretty much the scattering, because these kinds of pores, they can scatter the wave quite a bit. And then if you have, let's say, we now don't talk about closed cracks. If these are real cracks which are open, you are going to get T2, which is slightly smaller than T1. No, it's larger, I'm sorry. The velocity is smaller. T2, which is slightly larger than T1, and also A2, which is slightly smaller than A1. So it becomes similar to the pores. If these are closed, these differences becomes very, very small. We haven't talked about reflection yet, but the non-destructive evaluations that use wave propagation pretty much use these principles. I mean, we haven't talked about reflection so far, but this is the basic principle. Now, this is an application in structural health monitoring. So what you would see here is the y-axis. Let's look at this carefully. On the top, we are seeing a history of different earthquakes. So the x-axis is time, y-axis is the roof displacement of a building. And then those are different earthquakes. Okay. So at the bottom, you are looking at frequency in hertz. The frequency Fcs refers to the resonance frequency of the building as it is. That means that the building and the soil surrounding its foundation, the whole thing. F1 is kind of a different frequency. It is the frequency of the building itself. Now, how you get this frequency is very complicated. It's its own science, but I explain it very, very fast. That you can calculate, if you have accelerometers at different floors, you can basically see how the wave propagates from one floor to the other. So that frequency is obtained between the roof and the ground floor. So it doesn't include what is happening in the foundation of the building. It comes from the building itself. You have to calculate impulse response, and then this is now going from roof to the ground and the other way around, and you can see that, you kind of see the wave propagating. This is how F1 is calculated. Just, you don't need to know the details. Just accept that F1 is related to the building itself. F6 is the whole thing. So you have only one accelerometer which gives you everything about the whole system. So look at this graph and see what your observation is. What are you seeing here? Mahbube, lead the conversation. So what is happening? Now, in the very first one, when we have the San Fernando earthquake, what happened to the resonance frequency of the building?
So both of them is reducing over time.
Right. So the frequency is sharply dropping, right? It goes, it becomes many, I don't know exactly how many percent, but it goes from, let's say, 1.2, I would say, it's more than 1.3. It goes to 0.8, right? It becomes, goes very much down. This is when this gets also damaged, so they repair it. Because as you know, the frequency is related to the stiffness. So the building, when it loses so much stiffness, something terrible has happened. This is a structural health monitoring application. So they just look at the frequency of the building. Mm-hmm.
So for the Landers earthquake, which isn't that much higher, the reason why F1 isn't reducing that much is because it's not strong enough to damage it.
Mm-hmm.
It shakes, but it's not strong enough to damage it.
Mm-hmm. So exactly. So that's exactly it. So people use frequency of buildings and bridges to monitor what's happening to them during the large events. Now the difference between F1 and F6 is one is really from the building itself. The other one, it also includes the surrounding soil. So F1, this paper argues that F1 is a better measure because it's just from the building itself without, all these. It is like in our nonlinear experiments when we don't have bonding. If we could get rid of all the artifacts from bonding, pretty much this is what it is. So you, as Mahbube pointed out, in other earthquakes, sometimes you see a small drop, but it kind of goes back up. And in the very large earthquake in Northridge, it drops significantly again, but it's kind of recovering afterwards. It's going up. So this is just to show you that people really use this kind of yeah.
How come it looks like the San Fernando caused damage and it didn't recover, but then the Northridge one you're saying does recover, even though it looks like
they repaired it? It could be because they repaired it.
Yeah,
They just This is 1967, so I think they made a lot of change. This is in California. This building, they did a lot of retrofitting after those big earthquakes. This would be my guess. I just want to show you applications so you remember. So here, basically, I wanted to show you that you can use even this kind of wave propagation in the building, and they are arguing that it produces better results. So this F1 is coming from the propagation of waves inside the building. It's not coming from resonance. So F6 is the resonance. F1 is kind of the equivalent resonance frequency, which comes from really looking how the waves are propagating inside the building. And the argument is that it's a better measure for structural health monitoring. There are a number of studies like that in buildings. You can go and look it up. If you look at the references of this paper, you will see some earlier studies. The first one, I think, is 2006. So they are not very old, but it's a dynamic research area. Now, ultrasonic testing applications. Going back to the honeycombs, I showed you that this resonance and impact echo wasn't that successful in finding the honeycombs. So we used the system that you have seen in the lab. And this is a shear wave transducer. So the way it works is that you move it next to itself. This is a video, but here we don't see it. You move it next to itself, and if you go over a reflector, you are going to see a reflection. And if you put all of these A scans next to each other, you are going to get a B scan. Right now, I don't want to talk about reflection too much, more about velocity. So this is a different kind of ultrasonic measurements than what we did in the lab. What is the main difference you see here? Yes, this is one difference. That this is definitely a different transducer that we used before. But what is the main difference? People, what's the main difference? Okay, how did you do the other ultrasonic tests before?
I got like a sender and receiver.
It's the same.
Okay, so what is different here?
It's just one device.
One
Yeah, this
receiver.
is the sensor is different. They actually all shoot together. This has a lot of heads because you want to have a lot of energy, and that's how it is. But Mahbube, what were you
Yeah,
saying?
that was it. That's the same. There's a number of senders. That's it. But we had one sender, one receiver.
Okay, I put that in under the umbrella of the sensor is different, definitely. What is fundamentally different in this kind of data collection than what we did in the lab.
This is like a mesh. Yeah. The one we used is just a curve.
Could you please repeat? I didn't understand.
This result is like an image.
Mhm. But if we,
like just a curve.
if I moved your two transducers, I could also make an image, couldn't I?
So this uses a reflection of the signal, and in the lab we just directly.
Exactly. So in the lab you had a sender and receiver on both sides of your sample. If you look at your notes, I call that true transmission. So you were transmitting through the thickness of your sample, correct? Here, it's a different method. This is called a pulse echo method because you have your emitter, that's another name for sender, and receiver both on the same side. So the wave goes in, comes back, and gets received. So why don't we use what we did in the lab here? Why do you think, why do using this one?
We're not. So we have to be able to have, both sides have to be available for the here we only have one side.
Exactly. This is a preferred method for field testing because of one-sided access. So if we compare this to site characterization methods, in geophysics, people drill holes sometimes, boreholes, and they lower down sensors. So here is the surface of the earth. You make two boreholes, and then you lower down geophones most of the time, or hydrophones, and you shoot from one, receive from the other. This is very similar to true transmission, what you did in the lab, right? But most of the time, you don't want to do that. You want to do everything from the surface. So you have your sender and receiver on the surface in most geophysical applications. So it would be similar to this pulse echo technique. Okay. Now, if we know what the thickness is, you can also calculate the velocity, right? Here. It's easy. You know what the path is. If you know the thickness, you know where your sender and receivers are, you can get the velocity. So what we did for this honeycomb project was doing exactly that. So here you can see this kind of a scanner. It's actually commercially available, so you can just buy any kind of a scanner, you mount your sensor on it, and this is inside this room. On the bottom is the slab. The weather has been bad, so that's why they're inside the tent, temporary tent. And you basically collect the data at different locations. So this time we looked at two different parameters. So one is velocity. It's inverted. So this is one, basically, this is pretty much like time of flight. It's inverted shear velocity for the same slab. And you see that at the locations where we have honeycomb, time of flight becomes larger, so velocity is slightly smaller. Is this clear? Another parameter we looked at was really attenuation. So you look to see what happened at the bottom of the slab. What is the amplitude that you would get here? Because if you have more attenuation because of the honeycomb, this will be smaller. So you have larger attenuation, basically. And they both give very similar results, I would say, because they are kind of related. So that's one example when you have really pores. Now, if we don't have pores and we have a collection of cracks, there are analytical solutions that relate the change of elastic properties to the density of cracks. So let's look at what this equation is about. So if we have a solid, in this particular case, we are looking at randomly oriented cracks. Non-interacting means that they don't influence each other. If we look at the behavior of one of them, the behavior of the ensemble is the summation of the behaviors. Okay. And they can be even filled with some liquid. Now, there is a really, really nice paper by Kachanov. It's basically summarizes a lot of different approaches. You have the reference here, how to calculate these quantities for different kind of conditions of cracks. If they're aligned, randomly oriented, if they're interacting, non-interacting, etc. The only assumption that is being made is that at the location of the crack, the displacement is not continuous. At the location of the crack, the displacement is not continuous. That means that the two lips of the cracks, they're not connected to each other. Basically, that's all it is mathematically. It's a really nice paper, I think. I really like it. So let's look at what these parameters are. So if we have a collection of cracks inside the matter, if the material, the matrix in the beginning, had an elastic constant E0, because of the presence of these cracks, the elastic constants will change to an effective elastic constant.
It's not modulus, it's an elastic constant.
It's also elastic modulus. We can call it elastic modulus. So here you are looking at Young's modulus and shear modulus. So please add the what is what to your notes. Now, nu 0 is the Poisson's ratio of the matrix. And delta is a parameter which describes the behavior of this fluid which is inside the cracks. So this is related to this compressible fluid. So if delta is very, very large, this relationship explains the change in material elastic constants if the cracks are dry. So if it becomes very large, delta over 1 plus delta is approaching 1, right? So it's easy to recover the equation. Now, if delta goes towards 0, it means that the cracks cannot be opened. They're constrained, as if they are filled, for example, with an incompressible fluid like water. Okay. So it is, we can think about it as saturated cracks. So basically we know that the elastic constants are changing when we have a distribution of cracks. So I've plotted here for you this same equation with the same assumptions. Here is delta E, that means the effective elastic constant over E0, the change in elastic constants because of the presence of the cracks, and the x-axis is crack density parameter. So you didn't ask what this is. This is basically, you define, let's say this is your crack. And the radius is Li. It's a penny shape. And you are looking at a certain volume of your material. It is called typically representative element volume. And that's what crack density means in this equation. Now, whether this is a good, this is something people have used historically to explain the concentration of cracks. If it is good or bad, that is to debate, but that's what it means. Now, that's in 3D. In 2D, I didn't give you the numbers here. I actually wanted you to guess. It's important to kind of visualize what this crack density parameter means. Like when it is 0.125, that means this much cracking. When it is 0.25, it's quite a bit of cracking, right? So look at the graph. Let's say for 0.2, in the very ideal case, if the crack density parameter is about 0.2, the change in elastic constant is, let's say, maybe 25%. And it's much smaller if you have water inside. So from these relationships, two things become clear. There is a relationship between change of stiffness and crack density. So if we have a way to measure stiffness that we know we have with measuring velocity, we can kind of back calculate the crack density in material.
You said if we have a measure of the change in modulus, we can determine something about the crack density.
Right, so look here, if we know we can measure E effective. This is what you measure when you measure, for example, velocity. And if you know E0 and the other parameters, you can recover crack density. So this makes it kind of official that if you have cracks inside the solid, you can see how the elastic constant is changing. But at the same time, you see that even for 0.2, this is plenty of cracks. But the change in elastic constant is not as much. And this, when you translate that into velocity, it becomes about half. So it becomes smaller. So basically, there is a relationship, but how sensitive it is, that is to debate. I guess we are going over time. So that's where we can stop, I would say. So then we want to look to see how velocity and cracking kind of relate to each other next.